If you don't already know me, my name is Renee Hlajek. I am a professor at the Dunlap Institute for Astronomy and Astrophysics and the David A. Dunlap Institute Department of Astronomy and Astrophysics at the University of Toronto. And I'm super passionate about the things that I'm going to tell you about tonight because they are basically my research interest. They're super fun and exciting, and they're the kinds of things that I think when we're not worried about coronavirus, we should be thinking about more. So I hope you'll enjoy coming along with me. Okay, let's just get started. So most of us, look up at the night sky and we think, if you're like me, you think, what is it made of? How do we understand the universe? How can I take the questions that I have when I've had that cocktail or two and make them quantifiable? And that's basically my job. My job is understanding what the universe contains and how it changes with time. So I kind of think of this as, in a sense, of having given the puzzle pieces of the universe. This is an image of the timeline of the universe, and we're going to put that in a little bit of perspective later. But my job is taking these puzzle pieces that seem all out of order and in some way putting them together in a scientifically rigorous way. But I get data from telescopes around the world, and then we figure out how to make everything fit. So one of the biggest questions that should matter to you as a cosmologist is, what is the universe made of? What does it contain? How is it changing with time? And how does that work? Oh, there seems to be a little bit of a delay. Okay, great, you can see me, great. So what is the universe made of and how is it changing with time? One of the first things that the universe is made of are baryons. Now, baryons is a funny name for really the stuff that we can see. So you, me, that mug of coffee in your hand, cars, trees, plants, and baryons are the names we give for kind of ordinary matter. Protons, electrons, and all that stuff combined. One of the key things about baryons, so this photo that you see was taken in a street in Toronto in perhaps a time when more of us were outside. But one of the key things about baryons is that either they shine, either they make their own light. So for example, depending on the temperature that you are giving off your own light. Or they reflect light. So one of the reasons why you can see me tonight is that the light from this room is bouncing off my skin. And so that I'm made of baryons, and so I am reflecting the light from the light bulb in my room. And so baryons, we think are the kinds of matter that we understand. And we want to know, well, how much of the universe is made of baryons? We know that not a lot of the universe is made of baryons. And in fact, this is another example of the fact that we're reflecting light. So I love this image. It's just a kind of stock photo, but it shows you, looking up at a building and the glass is reflecting all the light. And that's really how we know the building is there. Otherwise, we wouldn't see it if it wasn't reflecting this light. I'm from South Africa, and so of course, there has to be a giraffe in my talk because I love African animals. And so this giraffe you can see in normal light, and that's because the sunlight is bouncing off the skin of the giraffe. But if you actually looked in infrared light, you would see that the giraffe is also giving off infrared light because the giraffe has a temperature. So you and I are all giving off our own infrared light. And if we had infrared goggles on, you would actually see that I am glowing. And in fact, as a side note, this is one of the ways you can test if people have a fever, because you can look at them in infrared light and you can measure the temperature of their skin. Okay, so that's baryons. Baryons give light or off light themselves, or they reflect light, or both, typically a combination of both. And so how much of the universe is made of baryons? Well, we can do a cosmic accounting and make a pie chart that contains like all of the stuff in the universe, and we can divide it up into how much is made of various components. We think that all the stuff I've just described, all the baryons, which includes stars, it includes the Earth, it includes neutrinos, it includes gas in space, all of that makes up less than 5% of the total stuff in the universe, the total energy of the universe. Now, if you're shocked and surprised, you should be, because the stuff that I've just told you about is basically all of the universe that we understand. Everything else that I'm going to tell you about tonight is new research and is largely unexplored. We have a lot to do to try and understand it. And yet you can see it makes up the majority of the pie chart. Okay, so what else is there in the universe? How do we figure that out? Well, luckily we have our friend, Albert Einstein. So this is a little bit of a plug for a video that I've made. If there are any parents here that whose kids are not around, I encourage you to check out this lesson. It's actually a lesson about what I'm going to talk about today, but in 5 minutes. But Einstein had this great revelation, which was that we can figure out how the universe is curved and shaped depending on what it's made of. So there's this relationship between what the universe is made of and how the universe bends, basically. And that space basically is the theory of general relativity in like one sentence. Another analogy of this is, if we think of why the Earth is going around the sun, it's really because the sun itself is bending space-time, it's bending the curvature of space, and the Earth is then moving in a straight line in this space, which happens to be an orbit around the sun. Of course, you'll see here that the Earth is also bending space-time around it, and that, of course, it gives us the gravity of the Earth, which keeps us on the ground. So at the end of this talk, if you are really bored and you've just gone, COVID crazy, you might want to play this fun game. So take an empty wine glass. If it's a romantic evening, light some candles, and hold the wine glass at an angle to the candle flame. What you'll notice as you change the angle from a little bit to a full face on to the candle is that you'll notice that you get these cool arcs or lines. Basically, the light from the candle flame is being distorted by the lens at the bottom of your wine glass. And either it makes just like a little curve, or it makes a full ring if you get the angle just right. So one of the things that's incredible is we know this happens with lenses. So the bottom of your wine glass is acting like a lens and it's distorting the light. That's of course how contact lenses work and glasses work in a similar way. But the same thing actually happens if we have enough matter to bend space-time, because if you're bending space-time, then the light from any object that's far away will be bent by the big mass that is bending the space-time. And the cool thing is that we actually see very similar effects as we see in this image, but we see on a cosmic scale. So this is a galaxy cluster. It's one of the Abell clusters. And you'll notice the galaxies that you see that are kind of orangey and blobby, those are galaxies all in one cluster. So they're at the same place roughly in space-time. They're at the same redshift, and they are very massive. They're a huge collection of galaxies. Each of those galaxies contains hundreds of billions of stars, and there are many in that cluster. So it's a very, very large mass. The cool thing is that the light from galaxies behind the cluster is traveling to our eye, or the eye of the Hubble Space Telescope, which is what took this image. And that light is being distorted by the mass of this galaxy cluster. And so what you notice, if you look on the outskirts, you see these like streaks of galaxies. And those are actually galaxies that have been distorted. So if you looked at them from behind the cluster, they would look like normal galaxies, but their light has been bent in the same way. I'll go back one. In exactly the same way as the lens does. You can see those kind of streaks, but this time the thing that's doing the distortion is the mass in this cluster. Now, one of the reasons why this is a good example of dark matter, and maybe you're confused because you're like, oh, I see things in this picture. So what's dark about it? Well, if we add up all the light from the stars and the galaxies that we see, these big orange galaxies, we can kind of do a conversion between how much light they give off and how much mass they have, just by knowing how stars burn. And so we can figure out, count the mass of the stars in those clusters. And then if we measure how much mass we need to do the distortion, it's nowhere near enough. So we know that most of the stuff doing the bending of the light, most of the stuff bending the light from those galaxies is invisible to us. And that's why we call it dark matter. It's dark because we can't see it, but we can know of its effects. We can measure the things that it's doing to light. And that's how we figure out that it's there. It's kind of like if you get on the TTC or the subway and you sit, you feel the seat is warm, you know someone was there even though they're not there right now. So we infer the mass of the stuff doing the lensing from those wibbly images that you see around the edges. And we see this in lots of galaxy clusters all over the sky. So this isn't just one particular observation. So what you need to know about dark matter is dark matter distorts space like normal matter. It's just we can't see it. Another piece of evidence that we have for dark matter is taken from this really cool cluster called the bullet cluster. Now, this is an image of the bullet cluster just taken with optical light, light that you and I can see. And in fact, it's taken with the Hubble Space Telescope. There's nothing particularly remarkable about these. You can see that there are some orangey galaxies in a cluster sort of in the foreground, but there's nothing necessarily remarkable about that image. Any of the lensing now that's happening, any of this distortion that's happening of the background galaxies is pretty faint, and so it's quite hard to make up. However, if you work in lensing, you can actually make a map of, given the tiny distortions, what is the mass that must exist in this cluster. And this blue image that you see is a false color representation of that. So scientists measure the tiny deflections of the background galaxies, and they figure out there must be a lump of stuff here, and they just color it blue for our eyes. But you'll notice that there are two lumps. So what we think is actually there were two big clusters of galaxies that we think are going to be interacting, that kind of smacked into one another. And there are two separate galaxy clusters that have interacted. We can also use X-rays to measure the gas in this area. So X-rays are basically measuring hot electrons, and we can use X-ray telescopes in space to measure, are there any hot electrons in this area that we can't see just with visible light? And in fact, this is what we see. So this is a map made with the Chandra X-ray telescope. And this shows us the gas in the clusters. And now you see something that looks kind of different. It almost looks like the gas from the left has moved through and is now on the right of this cluster. You'll notice there's like a bit of a shock front, and it almost looks like you shot a bullet through one of those, through the other cloud of gas. That's why it gets its name, the bullet cluster, because it looks like one of the galaxies kind of shot through the other. But if we put all these together, we notice something really interesting. So the gas looks like it's interacting. The two galaxies have like shot through one another, and there's a lot of stuff happening, but the dark matter blobs are just sitting there. It's almost as if they were able to move through each other without really making a fuss. So that's what makes us realize that dark matter, it doesn't interact very often. If you were to take the analogy a little bit further, it's almost like dark matter is sort of socially distancing itself. It's moved through the galaxies have moved through each other, but they didn't really interact at all. There were no shock waves or big clumps that resulted. So this cluster gives us a lot of evidence for the fact that we know there's something very massive. These two blobs are very massive, but we know it's not behaving like the baryons. It's not behaving like the pink X-ray gas that you see, because there are no shock fronts. So dark matter doesn't interact very often. So what you need to know is dark matter acts like normal matter in the sense that it distorts images, but it doesn't interact. So if you were to shine a light on dark matter, you wouldn't be able to see it in the way you can see my skin, because it's not giving off light and it's not interacting with light much at all. Otherwise, we would see that in this image. And we see this in many different clusters and many different galaxies. Now, I say it doesn't interact often. We're hoping that it interacts just once in a while, very rarely, because if that happens, then we can try and search for it on Earth. And the way we need to do that is we build these huge, we fill up old mines and we fill them with different kinds of material, or we bury detectors deep in the earth so that we can separate all the signals from things we might get on Earth, in the hopes that once in a while, a dark matter particle will react with one of the particles we put in the ground and make a little flash or make a spark or give off some kind of particle a shower. And we do that in the hopes that we can detect what dark matter is. Because all the stuff I've been telling you up to now is telling you what dark matter does cosmologically, what it's doing to our observations of things in the sky. But I haven't told you what it is, and that's largely because we don't know. We have some theories for some particles that it could be, but a lot of what we're doing now in cosmology is building big experiments to try and, by chance, make a detection of a dark matter particle. If we can detect the particle, then we can start to think about what is its mass and how does it interact with the rest of the particles in the universe. But it's a really, really tricky game because we know that dark matter interacts so infrequently. It's like catching a sighting of a celebrity in a place you've never been. It's very, very rare. Okay, so how much of the universe is made of dark matter? Well, unfortunately, if we do the accounting of the universe, of everything that the universe is made of, and we do that by combining different measurements together, we find that dark matter makes up 25% of the total stuff in the universe. So we've got just under 5% of normal matter. We've got 25% of dark matter. That's incredible. There's a lot of stuff we don't know at all and don't understand. But we know that it makes up a large quantity of the total stuff in the universe. It's good that you may be skeptical and you may say, okay, well, how do we know that? How can we measure all the dark matter in the universe to figure out that it's 25% of the total? Well, we build telescopes that scan the sky in a multitude of ways. So this is a telescope that I work on. It's called the Atacama Cosmology Telescope, and it's built high in the deserts of northern Chile. And the Atacama Cosmology Telescope scans the sky in microwaves. So it has a microwave detector, and it's measuring light that comes from just after the Big Bang. This light gives us information about how the universe was very far in the past, and also how it's changing with time. Fundamentally, what we do is we measure the temperature of this light on the sky, because that tells us something about where the universe was clumping and how that's changing. And what we do is we make a map of this radiation. Let's see if this works. Yeah. We scan the sky and we sort of put our own galaxy in the center of the maps, and we project essentially longitude and latitude of the sky, this imaginary grid that you can see, and then we unwrap it to basically make the kind of maps that you've seen of the Earth. But this is a map of the sky with the galaxies centered along the midplane. And we can measure this light in a range of wavelengths: optical light, infrared light, and microwave light. And the microwave light gives us a picture of the universe in its very earliest times. And we can measure the temperature of that light on the sky. And the differences in temperature on the sky tell us something about the physics of the universe. One of the things that's interesting is that I showed you an example of a cluster where a big mass of dark matter was bending the light of the galaxies. And that's an extreme version, but really we see the same thing happening to the light from the Big Bang. So the light from the Big Bang, which we call the cosmic microwave background, that has traveled through all this stuff to get to our eyes today. And every time it encounters a big mass of dark matter, it gets a little bit bent. And so all of the little bendings all the way between the beginning of the universe, about 380,000 years after the Big Bang, all of those little bendings or deflections add up. And so the maps that we make of the sky are a little bit distorted. And they're distorted exactly because there's dark matter in the universe. So what we can do is we can try and figure out how the distortions were made to try and understand the mass of the universe. This image that you have showing up shows you the kinds of distortions. So you'll have to look really hard because the distortions are very, very tiny. But this is what happens when light gets bent because of the dark matter in the universe. We do a lot of statistics and mathematics to try and decode this bending and understand how it can tell us where the dark matter is in the universe and how much of it there is. And we use this as a way to weigh the dark matter in the universe. I wonder if there are any questions now. Oh, we had one question saying, would a snake give off their own light? Yes, a snake would give off its own light depending on the temperature of the snake. So you would have to, snakes are pretty cold, but everything gives off light. So the ground itself gives off light in microwaves. And one of the reasons why the picture of the telescope I showed you has a big dish, that dish is actually to shield the telescope from the light that the Earth gives off itself. It's giving off this microwave light. So everything around you that has a temperature glows, which is really cool. Okay, so we can use the bending of this light to tell us about the stuff in the universe. And using that kind of lensing analysis, the distortions are called lensing, we can actually measure how much the universe is made of dark matter. So that's how we figure out that 25% of the universe is made of dark matter. I should also say, of course, that I'm talking about one observation here, but there are many different observations that tell us that dark matter is in the universe. So that sort of answers one of the questions that came up. Gravitational lensing is not the only way. We also know that if you look at the way galaxies rotate, they rotate in a way that can only be explained if there's a lot of unseen mass. Otherwise, they would have a different, the stars would rotate differently around the edges than we see them rotate today. So we actually have quite a few independent pieces of evidence for dark matter, which is one of the reasons why it's such a conundrum. If it was one observation, we could maybe say, oh, well, maybe they made a mistake. But really, all of these different pieces are giving us a hint that dark matter is there, and that's why we need to understand it. Okay, so what about dark energy? If you looked at the pie chart, of course, I said 5% is made of normal matter, or baryons as we call it. And another 25% is made up of dark matter. So that's only 30%. What else is there? Well, a little bit of foreshadowing. The rest is called dark energy. And I'm going to tell you a little bit about dark energy now. And the key thing I want you to take away from tonight is that dark matter and dark energy are not the same. Okay. So anyone who has kids, and I know that there are lots of kids at home right now, knows that if you throw a ball up and you drop it in the ground, it will hit the ground. And we know that that happens because of gravity. Now, I've just been discussing dark matter, and dark matter acts like normal matter when it comes to gravity. So if the Earth was made of dark matter, the same thing would happen now in this picture. Oh, we had a really good question that I'm just going to answer. The question was, if dark matter makes up 25% of everything in the universe, why is it so difficult to detect? That's a really great question. It's because it is so weakly interacting. It's kind of like if there was a crowd of people, none of whom wanted to speak to you. There could be a lot of people, but you wouldn't have an interaction. So even though there's a lot of dark matter, and in fact, there's dark matter passing through your body right now, it isn't interacting with you, which is why you don't notice. It doesn't hit your atoms, it doesn't interact. And so we have to really search very hard to find it. Okay, so, but it does interact gravitationally. So if you and I were made of dark matter, we would still be attracted to the Earth in the same way. We just would be invisible. So how do we understand normal dark matter and normal matter interact gravitationally in this way? If you drop something, it will fall. Now imagine if you started the live stream today and I dropped a ball from my hand, but instead of it falling to the ground, it floated away. Hopefully you would be skeptical and you would think that maybe I had added some air to the ground or something. I had pushed this ball away, because we don't know anything that would do that would work against gravity, right? We understand gravity. Anyone who's older than about a year old understands that things fall to the ground. But imagine if I told you that about 22 years ago, we made observations that seemed to give us exactly this kind of contradiction. I'm going to go into a little bit more detail about this, but let me tell you a little bit more. So in order to I should backtrack a little bit. I should say we made these observations about 22 years ago that I'll discuss in a second. And what we found is that there was something in the universe that was acting in the opposite way to the way we would expect gravity to behave. Instead of attracting things like gravity does, it was pushing things apart. And we call this dark energy. So dark energy behaves nothing like dark matter. It's very strange. It's much better to think of it as sort of an anti-gravity force. Okay, but let me tell you how we discovered that, because I know your minds are probably exploding right now. Imagine if you were on a dark street. There are no street lights. This image was taken in New York City when Hurricane Sandy knocked out all the power, and there were no street lights at all. However, there were still cars on the roads. So in this image, there's a car coming towards you and all you can see are its headlights. Now, of course, if you were trying to cross the road, you would know that that car is pretty close to you and you wouldn't cross the road. If you saw very, very dim headlamps, then you would think, oh, the car is pretty far away and it's safe for me to cross the road. Have you ever asked yourself how you know how to do that? How you can relate the brightness to the distance? We all just do it automatically, especially if we've grown up in a city. One of the key things is that it relies on you assuming that the headlamps in the car are all the same brightness when they're put in the car. That's why we take our cars to get tested for their roadworthiness, because headlamps have got to be the same brightness for everyone intrinsically in the car. If they weren't, then you wouldn't be able to relate the brightness of the headlamps to the distance that the car was away from you. And we do this all the time. But what if I told you that there were objects in space that act exactly like these headlamps, that have the same brightness everywhere in the universe? The cool thing is that we can then use those objects, if we measure how bright they appear to be, and we know how bright they should be, we can do exactly the same kind of calculation as we do on Earth. We can measure the distance to those objects. And that's exactly what we do. We take observations of very bright stars that we know all have the same brightness intrinsically, and we use how bright they appear to figure out the distance to these objects. Okay, but how do we find these kinds of objects? They must be pretty special. Well, in fact, they are pretty special, and they're called type 1a supernovae. And they're exploding stars that explode. There are many different ways we think that they could explode, but one way is that they exist in a pair of stars, and one of the stars pulls matter off the other star until it can no longer support itself from collapsing, and it explodes. Now, the trick here is that all of these stars explode when they're roughly the same mass, which means they burn with roughly the same brightness everywhere in the universe. This image that you see here is a beautiful image taken by NASA's Hubble telescope. And you see the beautiful disk of the galaxy, this like dusty disk of the galaxy. But the star that is important in this case is the supernova at the bottom, the bright star right at the bottom of the image. And this star is a very, very energetic explosion. And these are very bright objects that we can see all very far out into space. And so we do that. We measure how bright they appear, we know how bright they should be, and then we figure out what is the distance to these objects. If we do that, we notice that the universe, in order for them to be where they are, if we decided if the universe was only made of dark matter and normal matter, we could predict where they should be. But we find that they're not at the right distance. They're not at the right distance if the universe is made up of only dark matter and dark energy. And so we actually realize that this gives us some evidence that there's something else making the universe expand, making it expand much more than we would expect if there was just dark matter and normal baryonic matter in the universe. Now, we don't know what it is that could be making the universe expand so fast. And so we call it dark energy, but that darkness is just reflecting our ignorance. We don't know really anything about what it could be. It's definitely not a particle like dark matter. It's something else that acts anti-gravity. Okay, so how do we know that? Well, let's look at the observations a little bit more. This graph is sort of what I was trying to explain in terms of the distances. So we can measure the kind of age of the universe, which is on the bottom, and then the size of the universe, which is on the y-axis. And if the universe was just made up of normal matter, you would expect the universe to start, expand, and then at some point, all the stuff in the universe, the gravity of all the stuff makes the universe contract again. And that, until about 22 years ago, is what we expected would happen. We expected we'd be able to see when the universe would start to collapse. But we made these observations of type 1a supernovae, and we found that instead, the best model that fits is that the universe starts to expand, as we understand, and then at some point it starts to accelerate. So not only is it expanding, but that expansion seems to be speeding up, and it's speeding up now. And that allows us to quantify how much of the universe we need to be made up of dark energy to be doing that expansion. And it's around 70%. So most of the universe is made up of this stuff that's making the universe expand in an accelerated way and is acting against gravity. How do we detect that in another way? Some people say, oh, supernovae are the only way. If that's true, there's something wrong with the supernova data. But actually, the same bending of light that I told you about from dark matter also tells us something about dark energy. Let me answer a question before I continue. Yeah, so the question was, why are all these supernovae exploding at the same mass? That's a really good question. The mass, in case anyone is interested, the actual name of the mass is named after a famous Indian astronomer called Chandrasekhar. And what happens is the star that is sucking material off the bigger star, if it's living in its companion, it's pulling off material because this star is a white dwarf, which is a very massive and very small star. And the gravity of the star is so strong that in fact, it's sucking this material off its companion. But because it's so massive, if you add more mass to it, the gravity gets stronger. And basically this little white dwarf is trying to stop itself from collapsing. It can only really support itself against collapsing until it reaches a certain mass. And that mass is called the Chandrasekhar mass. Once it reaches that mass, there's just too much stuff. It basically implodes and then it explodes. Now I'm skipping over some of the details. Of course, there is a little bit of variation, but there is this tight relationship in the mass of the star and therefore all the stuff that is ejected. Okay, so supernovae are one way that we measure this dark energy. But also the bending of light that I told you about before is another way to measure this, because the universe, as it expands, it changes how the clumps of dark matter can form. Because as the universe expands, dark matter kind of can't get together to clump. And so we expect that the bending of light that I talked to you about before will also change if there's dark energy. The same lensing pattern that you see will be different if the universe has some dark energy in it as well as some dark matter. And we make a lot of predictions. Some of my job is to make predictions for how the universe would look if it had these components in and then fit it against the data. And so I'm going to tell you a little bit more about some of the telescopes that we use. In order to take ourselves to the next level of understanding, we need to figure out how can we take measurements of the sky to give us a good way to really constrain and measure these properties, because these are tricky things and they're subtle effects. So we need to get more data to do that. Well, one way that we do that is we build big telescopes. One that's currently being constructed is the Vera Rubin Observatory. So it's named after the astronomer Vera Rubin, who was a pioneer in studying dark matter in galaxies. This telescope is being built in the deserts of Chile. And you see here, it's partly under construction. It's a little bit further along actually by now already. And it will start taking data in the next few years. And this is really, really exciting because it will completely change our map of the sky. We'll be able to measure billions and billions of galaxies in the sky. In order to do that, you need to make a super huge mirror. So this is an 11 diameter mirror that's being driven very, very slowly all the way from Arizona. It's then put on a ship and shipped all the way to Chile on the BBC in Manitoba. And then it's taken off that ship by crane and driven up the mountain into the deserts of Chile and put into the telescope. So the mirror is now on site and we're continuing to build the telescope to prepare ourselves to make measurements of the sky. So one of the cool things about this telescope is how much of the sky it can see. So this is another image of it being constructed. And one thing you'll notice in the sky is there's a circle. And the circle is trying to tell you how much of the telescope, how much of the sky LSST on the Vera Rubin Observatory, this telescope that's been constructed, what is the field of view? So one of the ways when we build a telescope is we try to say, how much of the sky can this telescope see? That circle tells you the field of view of the Rubin Observatory. For scale, it's about 3.5 degrees. And for scale, the moon is about 1 degree. So that's the size of the moon is the way the size of the moon would appear in the sky. Another, a little dot, the tiny little square that you see is the size of the sky that Hubble can see. So the Hubble Space Telescope makes very deep measurements on a tiny patch of the sky. But the Rubin Observatory is going to be able to scan the whole sky very, very fast. In fact, it will be able to make one map of the sky every 3 days. And that means we're going to be able to make a deeper and deeper map if we keep looking at the same part of the sky. Okay, we have some questions. There was a question about, is there a pattern of how dark energy affects dark matter? There is actually. So one of the cool things is that dark matter clumps in the universe, and so we can predict the clumping, and dark energy slows the clumping down by quite a lot. So we use the clumping of dark matter and to test really how much the universe is expanding, because that clumping is made slower. And so there's a pretty distinctive pattern depending on what model of dark energy you assume. I'm assuming a very simple one for this talk, but you can actually make a prediction for how you expect the clumping to change if you have dark energy. We had another question is, do we know why everything gives off light? What generates it? We do know. So the matter in the universe, baryonic matter that gives off light, one of the reasons why it gives off light is because everything has a temperature. And we actually have, the understanding is that if you have a thermal temperature, that you give off radiation. Now, the laws that govern baryonic matter are the laws of kind of electrodynamics. And those tell us how we can relate the light that is coming from an object to the mass and the other properties like the temperature. Similarly, we know we can relate how fast particles are moving to their temperature as well because of thermodynamics. So the physics of why things give off light is pretty well understood. The physics of why dark matter doesn't give off light is slightly less understood, and we need to understand that a little bit more. Okay, so the Rubin Observatory is going to scan the sky and make a map of the sky every 3 days. Now, what is it going to use to make a map of the sky? It's going to use a huge camera. So this camera will have 3,200 megapixels. So imagine your phone, but now imagine it's basically 3 billion pixels looking at the sky and taking a picture. And so we are going to measure billions and billions of galaxies out to incredible distances in the universe. One of the cool things is that because we're making a map of the sky every few days, we're also going to detect new supernovae that are going off in other galaxies. Because if I take a map of the sky today, and then I take a map of the sky in 3 days' time, I'll notice there's a bright thing that wasn't there before. That bright thing is probably going to be a supernova. And so I can measure these supernovae all over the sky. So we're going to go from measuring a few thousand supernovae to measuring hundreds of thousands of supernovae on the sky. And this will be able to tell us exactly how this dark energy is changing, because we'll be able to measure them out to very far distances and also measure them on the sky. And this is some of the work that I work on. We also need to build new telescopes that measure the microwave sky. So I told you earlier that we measure this lensing, this distortion of microwave light. And in fact, the finer and finer resolution we can make and the deeper and deeper we can measure this light, the better measurements that we can make of the lensing and other properties. One of the cool things about these telescopes is that we are measuring light with the Simons Observatory. So the Simons Observatory is a new microwave telescope. It's not the same as the Rubin Observatory that I just mentioned. The Rubin Observatory uses optical light. The Simons Observatory uses microwave light. So as a scientist, I want to use all of the radiation in the sky, radio waves, visible light, microwaves. I want to use all of the data I can to build up a picture of the universe. And the Simons Observatory is one that we are constructing to build in, to measure microwaves. We're measuring these microwaves from the cosmic microwave background, but the cosmic microwave background is incredibly cold. So I talked about temperature and the light that you give off. Now my body temperature is about, I don't know, 25 degrees right now, which means I'm close to 300 Kelvin. 300 Kelvin is a sort of room temperature. Absolute zero, the coldest thing that you could ever possibly theoretically even measure is 0 Kelvin. The cosmic microwave background is only 3 Kelvin. So it's almost the coldest thing that we can measure in the universe. And so we need to build these telescopes with incredible precision so that they can make tiny, detailed maps of the tiny fluctuations in the temperature of this radiation. And so all of the efforts that we're doing are to not only understand the universe, but to measure it with more and more precision and accuracy. As we do all these things, and before I finish, I will ask this question. So anything, oh, someone was answering it. Yeah, anything that has a temperature above absolute zero indeed has molecules moving and gives off light. Thank you, Babak, for answering. So I've told you that we have dark matter in the universe that is invisible but acts like normal matter in the sense that it is attracted to things gravitationally and it bends light. I've told you about dark energy, which behaves nothing like dark matter, and it acts against gravity and appears to be making the universe expand at an accelerated rate. We have lots of components in the universe, and part of my job is coming up with new models and trying to see if I can disentangle the puzzle pieces of the universe to understand the whole picture, where we think the universe started in this hot phase, and then slowly galaxies and stars started to form, and eventually we find ourselves today in the present day in an accelerating universe. I hope this has made you think a little bit more about the universe, what the universe is made of, also about how it's going to end. And I'm really, really excited. I want to take lots more questions now, but thank you for listening. I'll wait a little bit for questions to come in. Don't be shy. We have lots of time. Thanks so much for coming, folks. As I wait to take questions, I also want to remind you we're going to be doing these chats regularly, so please make sure to check online. They may be at different times, so we'll make sure to advertise so you know when to take a look. But we encourage suggestions, things you want to know about. We really want to make sure that the following few weeks and months are as enjoyable and enriching for you as possible, because we want to talk about space and we want to talk about it to you. So we had a question. What do I think dark matter is made of? Ooh, that's a good question. So I didn't put in my own theories of dark matter, but I work on an amazing particle. I study an amazing particle called the axion. So the axion is a very light scalar field, which is a type of sort of potential particle dark matter, but it's very, very, very light. And so we need a lot of it in the universe. And so some of my work is trying to see if I can explain these observations that I told you about, if the universe was made of axionic dark matter. They are really, really exciting. They're motivated by particle physics, but we haven't detected any axions. So the jury is still out. Chris said, how do we know that dark matter isn't dark baryonic matter like rogue planets? That's a really, really good question. So some people said, what if it's just a bunch of black holes? The problem is that there's really not enough. In order for you to have the amount of dark matter that we see, you would, if there was made of, say, rogue planets, or some people talk about massive compact halo objects or machos. If the universe was made up of these kinds of objects, you actually could make predictions for what you see, and it doesn't really quite fit. So those objects were a proposed candidate for dark matter, but unfortunately it doesn't really fit the observations that we see. We would see a very different sky in the cosmic microwave background. Another question is, how does the construction of the telescope isolate different parts of the spectrum? How is it that infrared telescopes are different than optical reflectors or microwave telescopes? That's a great question too. So typically the way the telescope is constructed, there are a few things. So you build a certain detector that is sensitive to certain radiation. So in our case, we build bolometers that are sensitive to microwaves. The physics of how those bolometers work is very different from the kind of telescope that would be measuring optical light. One of the ways that we want to do is measure very fine changes in the temperature of the radiation. And we do that by measuring these detectors that are very, very, very sensitive to temperature. We also have different kinds of radio antennas that you build to measure microwaves. So there is optical light shining on our telescope all the time, but our detectors are not sensitive to it. Conversely, the Rubin Observatory is built with specific filters that measure only one little piece of light, kind of like you can imagine if you put a stained glass window. It's not exactly the same, but this, the light is only coming through in a particular waveband. So we build it up that we're only sensitive to one part of the spectrum at a time. And then you can measure different spectra of light and different colors of light with one telescope. And so one of the exciting things a lot of people get into is telescope design. And it really depends on what you're interested in terms of what telescope you build. There's another question, which is, how do we know if dark matter is only one type of particle, or could it be several diverse types? We don't. That's a really good question. So there are lots of people who study lots of different models. My colleagues and I like axions, but other people are studying weakly interacting massive particles, or WIMPs. And we don't know until we have, one of the jobs that we have as scientists is to figure out what is the difference between my model and your model. And if they all predict exactly the same stuff, then it's very difficult to tell them apart. And then sometimes what we use is Occam's razor. We just say, let's go for the simplest model right now. But as soon as we get more data that seems to conflict with the model that we have, then we have to refine our model and change so that it fits the data. Great. If you're interested in studying dark matter, I encourage you to keep studying, because there's a lot of cool stuff we need to learn. So what is the next breakthrough that astronomers and astrophysicists are hoping to see soon? Well, I am really hoping that we do, in fact, make a detection of dark matter. We have a lot of different telescopes looking for lots of different potential particles in various ways. So scientists are creative about thinking, what if dark matter interacted a little bit like this? And what if it did that? And so my hope is in the next 10 to 20 years, we actually do make a particle detection of dark matter. Similarly, the Rubin Observatory is going to take us a long way into understanding what dark energy does to observations. It still will be hard to tell us exactly what it is, but we'll be able to tell it what it does. So for example, you don't know everything about me, but the fact that I have an accent tells you something about me. And the fact that dark energy does certain things to objects in the universe tells us something about it. And so we need more and more information. And the Rubin Observatory is going to operate for at least 10 years and will give us this incredible amount of data. So I really hope that in the next 10 to 20 years, we're a lot closer to knowing what dark matter and dark energy is. We have a question. Have all supernovae been measured to have slower acceleration that are attributing to dark energy? And is it all supernovae, is this just a difference of the cosmological constant? So yeah, if it was only supernovae that measured dark energy, then we could say, well, there's something wrong with the supernovae. Yes, the model that I've been talking about tonight has been the cosmological constant. But of course, we are trying to constrain more exotic models of dark energy with some of this data. The issue is that it's not just one type of data that actually tells us that the universe needs to be accelerating. Now, you could say maybe it isn't dark energy. Maybe gravity is just getting weaker in the past or in the future. And those models are allowed. They're slightly more complicated, but they're definitely, you could say, I don't want dark energy, let it be something else. There's a lot of theoretical space, but we now have many different observations. We have the cosmic microwave background, we have the lensing of the background, we have the supernovae, we have other observables I haven't spoken about at all, including the clustering of galaxies. So we have lots of different pieces of evidence for the acceleration of the universe. Yeah. The question of what is the universe expanding into? Yes, we had a great lecture from Dr. Mike Reed from last night about the idea of of the universe expanding into something, and how that's really difficult to get away from, because as humans, we're so used to putting ourselves in a space and then thinking of the universe expanding into that space. So I encourage you to watch the misconceptions about the Big Bang episode from yesterday. It was really great. We had a question about, do I believe that there are multiple multiverses? Do I believe in multiple universes? So that's also a great question. We have, I didn't really get into it, but there are some models of the universe that say that, that describe how the universe got really big very quickly, which we call inflation, or as a name for it can be inflation. And some models of inflation predict that there are multiple universes. Now, one of the tricky things is, as a cosmologist that works with data, is I want to test those models. So I don't just want to say, oh, the multiverses exist, but I want to think, are there ways to test it? One way potentially to test the multiverse, or really to test string theory, which often suggests a multiverse, is through the axion. Now, I didn't get into this in any detail at all, but some models of string theory have extra dimensions, and those dimensions are very small, and the thing that makes them small can give you an axion. So in a way, by testing and looking for axions, I'm trying to say, if I rule out, if axions are definitely not in the universe, then it means that our models of string theory are slightly more constrained. So great. Thank you so much for joining us, folks. Make sure to tune in again and check our website for more episodes coming up. And have a really great evening. Thank you so much. Bye.